want to make sure that this is with the iodine copper, right?
It actually goes with the last one.
With the titration one?
Or the equilibrium law that we're doing today.
Oh.
Yeah, so you could hang on to it.
Okay,
yeah.
sounds good. I was like, ah. Thank you.
So I'm not sure if I'm calculating it wrong, like in my calculator, but my answer versus the question answer is a lot different. It's the 1.8 and I got 5.32. And I've tried inputting it in my calculator a few different ways, and I keep getting, I've gotten...
Wait, do you multiply across? Because these should all be like equal to each other. Though. That's what I think is funny.
Oh.
Yeah.
So it's not multiplying.
No, it's just saying that, I think it's saying no matter which one you pick, right, that you can pick whatever rate, and that will give you the same answer of the 1.8. So yeah, don't multiply them, they're all equal to each other.
Oh, okay, I see.
Yeah.
So where does the negative 4?
Oh, once you do the division on any of these, then you get the factor of -4.
Oh, I see.
Yeah.
Thank you.
All right, let's get started here. So happy Tuesday. And then, if you can believe it, we're at week 9 here. So again, just a quick recap of where we're at in the term. So of course, this is week 9. So we'll introduce equilibrium today. And then week 10 is going to be acid base plus a little bit of equilibrium, and we'll kind of keep this equilibrium theme going to third quarter as well. So we're really almost at the end here. I feel like it snuck up on us. And don't forget, very loud truck, that your paper is due ideally by the end of week 10. I'll just put on there Friday. So either paper copy to my inbox or email, either one of those. And so don't forget lab makeups. I wasn't planning, well actually, yeah, I wasn't planning on being around on Friday, but I could be around this Friday. This Friday I have availability, but let me know. I know some people are also making up lab during the Tuesday, Thursday section, so that's good. So just let me know, and let me know which labs you're making up, because especially these last two ones, and y'all know that did them, you know, they have a time element to them, so they're a little bit sensitive to solutions. So if you have to make up a lab, we may have to prepare them or test the solutions. Then any other last thoughts, questions? Oh yeah, if you attended the guest speaker, I'll try to see if I can hunt down the in-person list, but you should probably email me just in case if you went in person. And then the video actually ended up on my YouTube channel. I don't know if y'all saw that. So you should be able to find the link so you can watch the video. And again, just email me like 1 or 2 sentences, just so I know that, you know, you watched it, whatever. And then in terms of grades, so I think I got caught up on the quizzes and the homeworks. I haven't graded anyone's labs and stuff. I have a few no names though, so I'll post those up either at the end of class or the middle of class or during lab. So yeah, if you're missing your homework grade, check your name. All right, other questions, comments, logistical things? All right, so let's, again, now we're kind of recapping where we're at. So of course, right, we've been studying how fast things occur. And so now we're going to study how far, right? So now we're saying, you know, does this go to completion? You know, is there some sort of equilibrium we'll introduce? And so kind of figuring out this products versus reactants ratio now. And so kind of before we dive into things, let's just remember a couple of arrows. And so basically, we just don't want to confuse resonance with equilibrium. And so remember, resonance is this double-headed arrow, and that's to show electron movement. And again, with resonance, right, you don't break any bonds. We just kind of move these double bonds or move electrons around, and usually move pairs, right, a pair of electrons at a time. And so this is, of course, different from equilibrium that we're bringing up today. So our equilibrium arrows, and again, this is now used to show our reactants on one side, and then of course our products on the other. And again, right, we're trying to now quantify basically, right, how many products versus how many reactants we have. And so again, right, we need all the data for this. So something could happen really fast, but then maybe it doesn't go to completion and it's just kind of stuck at a 50-50 mixture. So again, right, you have to have data behind all these things as well. So we'll be seeing that. And so let's look at hemoglobin and what hemoglobin is. And so those of you who are more biology inclined can always chime in, but essentially hemoglobin is a protein that's found in red blood cells, and of course it binds with oxygen. And so we can just think about that equilibrium process. And so of course we can imagine, let's just say this is in your lungs, and then if you have a high concentration of oxygen, obviously you freshly breathed it in, then it's going to bind, and then, right, this is your new product. Then your hemoglobin-bound oxygen, right, travels all throughout your body, maybe to your leg, and then of course your leg is going to have not a lot of oxygen, right, because it probably was using that oxygen to move. And so then, right, again, our equilibrium arrow shows that it can go back and forth depending on the conditions. And so, of course, oxygen is released in your limbs, and then the hemoglobin, right, cycles back to your lungs. And so this starts to, we're already kind of teasing Le Chatelier's principle, which we'll get into, but it's just a fancy way of, describing which way the reaction's going and, right, putting stressors on the system and having it react. So again, right, all we're saying is if we have a lot of oxygen, obviously it's going to bind, like in the lungs. And then when we have low concentration, we can say that it will unbind. And so we could also relate this to fetal hemoglobin and thinking about equilibrium and binding constants. So I updated. I had another paper before in those notes, but I actually didn't like it. It was kind of convoluted. And so basically, let's look at these structures. So it's kind of interesting. So this is fetal hemoglobin on the left and then adult on the right. And so they have pretty similar structures. And so it mentions the structure down here, which is interesting. So they have these alpha subunits, they're called, in pink. So those are the same. But then what makes the fetal hemoglobin bind stronger to oxygen is just what's called these gamma subunits. And because of this, basically, fetal hemoglobin has an increased affinity for oxygen. And of course, right, that makes sense. We can think about kind of why that is. And so many studies have proven this, that the hemoglobin equilibrium constant is larger. And okay, well, that kind of makes sense. So of course, right, mother is breathing in and also needs oxygen. And so of course, once the hemoglobin makes its way to the baby, right, part of the trick is, well, how is the mom going to release the O2 binding and the baby get sufficient ones? And because it has a more efficient binding coefficient, that means that it will take any O2 that is released. And so again, that's why the adult hemoglobin is able to release the oxygen and then bind to the fetal hemoglobin. And if we go back to this page here, it was kind of interesting because it mentions some other extensions for this. And so again, now we look at, so apparently there's a phenomenon where some adults have higher levels of fetal hemoglobin. And so what they found is that if you have fetal hemoglobin, it's not susceptible to the sickle cell mutation. And so they're trying to explore, they mentioned gene therapy as kind of a way of, maybe you could give people then who were affected by sickle cell some fetal hemoglobin, and that would, improve the symptoms. So kind of interesting to think about, especially those of you who are kind of more biology minded. So again, just thinking about the overall structures of the proteins and then how that relates back to these binding coefficients that we can quantify. All right, so that's our connection. And so now we're just kind of getting into, right, the theory behind it and just how we look at our reactions. And so, of course, right, if we're just doing a reaction, so we start our reaction, and in general, right, our reactions are consumed and products are made. And of course, right, that means our reactant concentration is decreasing. We'll get a good taste of this in lab today with the lab. It's a good one. And of course, right, at some point as your reactant concentration decreases, forward reaction rate decreases. We kind of know that from our rate laws, again, depending on the order, which is kind of our general statement. And so eventually, our products can react to reform some of the reactants, again, assuming that your reaction can go back and forth and has kind of this equilibrium. And obviously, right, not every reaction is reversible. So again, we'll see that. And so as our product concentration rate increases, and you could kind of think about just simplified structures. So just thinking of two things, binding and unbinding. So now we're saying, okay, our product concentration is increasing, and so that means this reverse rate will happen. So now A plus B, right, recombining to do AB. And so then, obviously, we're going to be studying reactions, of course, that are reversible. So obviously, not every chemical reaction is reversible or easily reversible. And then, so re-mentions are arrows. And so, of course, normally we worked with this single arrow convention. And when we say that, right, we're usually saying, okay, it's all converted. Two products, right, goes to completion. That's usually the implication with that. And then, of course, we're learning that our double-headed arrow means that it can go backwards and forth, and the reaction, right, can proceed in both directions. And so then what we're getting at this situation is eventually we'll reach, right, dynamic equilibrium. And so now dynamic equilibrium is just where the rates of the forward and the reverse reactions are equal. And so, right, then they have the same overall concentrations. Obviously, that's not to say that the reaction isn't going on, right? So still at an individual molecular level, there's smashing and combining and going apart, but the overall concentration remains the same. So concentrations of our chemicals remain constant. And so again, it kind of just walks us through how this happens. We can look at our graph again. And again, right, we're just saying, okay, we started this reaction. Looks like we're reacting hydrogen and iodine to form HI. So it's showing us our initial concentrations. And again, all this is to say that our reactants are being consumed. And then we can kind of see for ourselves, right? You can start measuring the tangential line there, but the rate, right, decreasing as the concentrations decrease, as our reactants are consumed. And then, of course, we can appreciate HI forming, and then again reaching our dynamic equilibrium state. And again, dynamic equilibrium, forward reaction equals our reverse reaction. So no overall change in concentration. And so now we want to just clarify, just because something is at equilibrium, right? We're not saying that there's equal amounts of products, so this is where our equilibrium constants will come in. So again, all we're saying is the rates are equal. We don't know what the concentrations are yet, but we'll be able to solve them from our equilibrium constants. And so we'll dive into kind of these general statements. So it says, right, some reactions reach equilibrium after almost all of the reactant molecules are consumed, but we actually want to put a number to that. And then, right, we'll see how that compares when only a small portion of our reactants are consumed. All right, so basically we need to quantify what we just said with K. And so I would definitely write this down right now, star this. So this is our general form of our equilibrium constant. And so notice, right, we have our reactants with our coefficient A for reactant A, coefficient B for reactant B. I'll zoom in on that. And so again, note the general form. You have products over reactants, and then everything should be raised to whatever the coefficient is for your balanced equation. So it says that there, so lowercase letters represents our coefficients, products over reactants. So I'll let you copy that down because that's essential. We'll need that form for everything we're about to do. Oh, well, right, this is just saying this is what the balanced equation is, right? And then that's how the balanced equation translates to your K. And so we'll get into, because not every reactant or product will be part of it, but we'll get into all those little details. But yeah, you just want this general kind of form here. Give people another minute. All right, we all have that copied. And so then this is again just our equilibrium constant. And then it does not have units. So it's just, right, our ratio, so unitless. All these will be molarity concentrations that we'll be plugging in. So either molarity or later we'll get into partial pressure, but mainly molarity. All right, so now let's just practice, or before we practice, we'll look at our example. So we have our reaction, and of course, these start to look pretty similar for these types of things, right? A lot of gas reactions and dimerizations and such. And so we have two equivalents of dinitrogen pentaoxide in our gas form. So note, right, in this case, they're all in the gas form. And that's important. So this is some sort of gas reaction, right? You can think about how we can extend this and apply our gas laws.
Does the equation still work if it's a liquid or solid?
Yeah, so that's where I mentioned, right, we'll just plug in either molarity or eventually partial pressure. And so then we can see how this translates. So again, right, they did it for us. So products, reactants, so obviously products over reactants. This is just our balanced equation. So our two equivalents of dinitrogen pentoxide give 4 equivalents of nitrogen dioxide, 1 equivalent of oxygen. So then equilibrium expression is just NO2 to the 4th times our oxygen, obviously to the 1, over N2O5 squared. So does that make sense to everybody? That's how we translate that form. All right, so now try to practice. Put that so. So express the equilibrium constant for the combustion of propane, and we are given a balanced chemical equation. So 1 equivalent of propane, so C3H8, plus 5 equivalents of oxygen, give us 3 equivalents of CO2 and 4 of water. So just take a minute, A, B, C, D, and then we'll poll the class which one's the correct expression. Try to zoom in a little bit more. So if you're in the chat, you can post A, B, C, D. Another few seconds to make your selection. So let's see. Who thinks A? What about B? Yes, everybody likes B. And any votes for C or D? So B looks good, and you could, of course, write it yourself. So products over reactants, so H2O to the 4th times CO2, oops, to the 3rd over propane. And again, they're all in the gas phase over O2 to the 5th, which match with B. So excellent. Questions on that one? All right, so that's generally kind of the easy part of what y'all will have to do, is just kind of setting this equilibrium expression up. And so again, we'll get into the quantification. So that's what you're going to be doing in lab today, is measuring some concentrations of products based off of our spectrophotometer. So that'll be fun, and it'll be like a real lab, and what you would actually do in like a research setting. And so then let's kind of look into what they were trying to get at with this value of K and what it's kind of telling us. And so now we're looking at this reaction, and this is H2 plus bromine gives us hydrobromic acid. That'd be a nasty reaction to actually perform. And so it's telling us, and again, right, you can set this up visually, just kind of products over reactants. You don't even really need to write the whole expression. Just, okay, products, reactants. And then look at this K value. So it's telling us, right, it's much, much greater than 1, but they weren't kidding, right? 1.9 times 10 to the 19th. And so again, just think about what that's saying, your ratio, essentially. I don't have it obviously properly down because I haven't fully quantified it, but again, just kind of putting, okay, reactants over products. So obviously in this case, right, our products are favored when K is much, much greater than 1 there. So that's telling us, right, this reaction is mainly going to go to completion. So expect, right, high yield from this. And then, of course, now if we have, this reaction, so nitrogen plus oxygen gives us NO. Again, products over reactants. So now it's saying K is much, much less than 1. And again, in this case, they really weren't exaggerating. So 4.1 times 10 to the negative 31. Although that's probably a good thing, right, that this is such a low equilibrium constant, or else we probably wouldn't have any oxygen to breathe at normal air. But yeah, so obviously, right, we're not going to get a high concentration of NO, and again, that's good for us oxygen-breathing creatures. And then, of course, right, I didn't put it there, but obviously, right, we can think about if K is about 1, then obviously, right, we're saying that our products and our reactants are pretty similar. Obviously, they're not going to be equal in concentration because I'm not taking into account all the little square things right now and the coefficients, but obviously, right, we're saying that, you'll get a mixture of both. So you can, again, think about the chemical engineering part of that, how you would have to push reactions. And so that's part of, again, right, the engineering part then of chemistry of like, okay, if you got this reaction, then you're probably in good shape, right? That's going to be very favorable. But if you're trying to produce, NO from this method, obviously that's going to be pretty difficult, and you might have to be creative, right, and kind of forcing it. And this kind of goes back to the Haber-Bosch process as well. All right, so see if we can look at this. So which of the following statements is false? So I'll give you a minute or so to read it and make your selection mentally. And if you're in the chat, you can post your A, B, C, D, E selection. So let's look through these statements. So let's read A. So K is much, much greater than 1. The forward reaction is favored and essentially goes to completion. So is this? So that's true. Okay. When K is much, much less than 1, the reverse reaction is favored and the forward reaction does not proceed to a great extent. So still true. So C, so K is about 1. Neither the forward or reverse reaction is strongly favored. And about the same reactants and products exist at equilibrium. So I see some nods. So that's true. And then D, so K is much, much greater than 1 implies that the reaction is fast at producing products. So why is it false?
There's no factor for temperature in the actual equation, so.
Or factor for rate, you mean?
Temperature is related to rate, so if you have two molecules that mix anyway, near sub-zero temperatures, they're not gonna mix very fast.
Yeah, or just, I mean, the fact is we need some sort of rate data. So yeah, we're given 0 rate data. So even though, it could be obviously happening on a very long time scale, right, that it's going to go all the way to completion, but yeah, it doesn't, we're given nothing about it, we're giving no temperature conditions, so we can't conclude anything about the rate. So good. So that one was false. And again, all this is to re-emphasize, right, that we need our rate law data for this, right? We can't just start assuming orders or rates or anything. We have to have data. And of course, same thing kind of for this equilibrium, right? So we're going to have to be given some constants or some molarity data to continue. All right, so now we can get into a little bit of relationships that will help us. And so this is just proving this statement down here, which we kind of already saw from our rate, but now we're re-emphasizing it for now our equilibrium is going to be the same. So of course, if we have this in the forward direction, again, products over reactants, so C to the C times D to the D over A to the A times B to the B. And then if we reverse this, so then it's going to be the inverse expression. So, right, we can see that already, that these are inverse. And so all that's saying is, okay, if we know our K forward, then that's equal to 1 over K reverse there. So that could help us for various problems. And so then if we have a coefficient of our reaction multiplied by a factor, then our equilibrium constant is raised to that power. So we could see this mathematically. And so, right, let's just say we have A plus BB gives us CC. So, of course, write our equilibrium expression. And then if we double it, right, that's essentially the same as squaring everything, or 2 times across, right, multiplying 2, 2, 2. And then if we now have to take it to the 2A, so these are equal. So therefore, if we have to multiply an equation by some factor, then we take it to that power. So of course, right, if we'd also taken it to the third or whatever, then we would take it right to the third power, whatever we needed to do. Well, it would change this K, right? So it changes K2. So just saying, again, we're squaring the value of K. Yeah. And that makes sense, right? So you double your reactants, so that would influence your equilibrium.
And when you're calculating that for a liquid, how do you format the concentration?
Molarity. Yeah, so it's always molarity or partial pressure. And we'll do examples. Right now we're just kind of laying out our relationships. And so let's say, right, we add 2 equations to get an equation. Then our equilibrium constant of our new equation is a product of the equilibrium constants of the old equations. And so it shows us the logic here. And so, right, let's say it's 2 steps. So we're going to go A to B, then B to C. But overall, right, we want A to C in that equilibrium and what that is. So we're trying to figure out K3 here, right? C to the C over A to the A. I'll just rewrite that. Or just what we're trying to find, our overall reaction. So then it's saying, okay, let's say we know K1. So obviously, right, this is the equilibrium expression. Then we know K2. Well, if we multiply these two, right, B cancels out, leaving us with our appropriate expression. So again, we can just multiply our two equilibrium constants, K1 times K2, to get our K3 one. Just write that down. All right, so now we can try this. And so now we have our famous Haber-Bosch reaction. And so we have our synthesis of ammonia, so N2 plus H2 gives us two equivalents of ammonia with an equilibrium constant of 5.6 times 10 to the 5th. And so what happens for the following reaction? So take a minute or two to calculate that. So what are we doing? What do we notice too about these two equations and what we have to do to our original K here?
What comes to half the power of the other equation?
So half,
Yeah.
all right,
So
and
based on what we just learned, you can take the square root of that K number and do the K one.
and what else do we need to do? Square root of it, and then what else do we notice?
One of them's split, the other one sort of becomes one molecule. So, what was initially two reactants on one side?
So
It's going to be the one over that.
yeah, so then this is just the inverse, right? Or we could say this is, the forward direction, in quotes or whatever, reactants, products. And then this is the reverse direction. So, right, just the same things. Our ammonia is now splitting versus, right, combining. And so what does that do to the K?
You get the reciprocal of that.
So the reciprocal or to the negative, and let me,
1 over 748.
and then, sorry, what was your K value?
I got 1 over 748 by 33.
1 over, what's that in decimal? So let me pull up my calculator.
I got a 0.001 336.
0.001,
336.
yeah, that sounds good. And let me just punch it in so everybody can see. 5 to the power, -1/2, which is exactly what you said. So 0.0013, and then we can round it. We have like 2 sig figs, so give it 0.00134 for our K prime.
It's inverse because we're doing the inverse function, not the lower.
Yeah, because again, we had started with N2 and H2, made us ammonia, and then we just did the reverse, right? So that gave us K to the -1, oops, or inverse, right? So K -1, and then we had to take it to our half factor. Does that make sense? All right, so let's keep going. And so now, let's see if you could figure out K1. So you're given these series of reactions. And so K1 is CO2 plus H3 equivalents of H2 to give us methanol and water. And we're also given these other 2 equations, so CO plus H2 give us CO2 and H2, and CO plus 2 equivalents of H2 give us methanol. So first think about, right, how to add these up to get what we want on top, and then what does that do to our Ks? So how do we have to add up these equations 2 and 3 to get to 1?
reciprocal of the second equation, which would just be the products and the reactants flipped around. And then you add the two.
All right, so let's, before we start doing the reciprocal, I'm just gonna do what you said. So, okay, you said we need to flip 2. So I'm gonna flip 2 just so we can verify that we get our 1 there that we're looking for. And I'm just rewriting 3, right? I can just add 2 or reverse 2 plus 3. And so again, just verify that that adds, so our COs cancel. And then we can see, okay, I have CO2 plus 3H2, okay, that matches, plus H2O plus 1 equivalent of methanol. All right, so now we can start continuing with what you said. So you said, okay, this means that this is K2 inverse, or -1. This is still K3. And what was the last bit you mentioned?
You just add them together, right?
Yeah, so they would be additive or such that we multiply them together. So then K1 is just equal to K3 over K2 at this point. And so now I'm just plugging in the numbers. Sorry, horrible handwriting. And so let me just plug it in. Of course, you can shout at me what you got. And see answer in the chat. So I got 140. Chat is showing me 140. And then is that what we got in here?
I added them together instead of.
Oh yeah, so remember to multiply them. And then we get that in here. Yeah, just don't forget to multiply formally. So that should be 140. All right, that's probably a good spot for a break. So let's take our 10-minute break or so. We'll be back at noon. And so we'll keep kind of plugging along. Hopefully the grades are posted. I should double check. I think all the grades should be posted. Oh, because remember when you take it to the negative power, it's like putting it on the bottom. Yeah, so I just, if you had punched in your calculator k to the negative 1 times k3, you would get the same. Great, it should be in there. It should be in there. Double check. Alright.
Click the calculator.
I blame Blackboard Ultra.
That's fair. It's reasonable.
So chapter 15.
Yeah.
Okay, fix that for you.
Thank you.
All right, I think we're almost all back. Well, maybe give, okay, there's our last few people. And then, so I'm trying to hand back the quiz. I'll keep working on handing back all your stuff, but double check the homeworks and everything. Yeah, Blackboard, it's not like Excel, this new Blackboard Ultra where you like hit enter and it's like ready to type. So sometimes I skip a grade here and there. So just double check me. I try to be careful, but yeah, Blackboard Ultra, not ultra features. All right, so let's continue. Oh, and like I said, there's a few homeless homeworks, so if you could take a look at them, I'll try to parade them around. I think I also have like old homeless homework, so if you still are like missing an earlier grade, double check with me. I just stopped parading around those homeworks. All right, so let's kind of continue. And so now we just want to make the relationship of our equilibrium constant to gases. And so again, right, like I said, you can either use molarity or we have our gas law expression. And so there's a little nuance between them. And so we'll look at that. So obviously we've mentioned this kind of before in our gas laws chapter. So okay, the concentration of a gas in a mixture is proportional to its partial pressure. And so therefore we can express our equilibrium constant as a ratio of these partial pressures. And so again, right, same expression, all we're saying is all these reactants are in the gas phase. So right, that's different than when we're doing it in molarity, right? Then all we're saying is all our reactants are in solution phase. We can essentially treat it the same. And so again, right, you can see basically the same format. We just have, right, instead of molarity, then we have partial pressure. And so then the trick comes into play if you wanted to try to convert between the two. And so let's just continue following through. So it says here that our partial pressures are always in ATM. And so obviously, right, KP and KC could be different because of our unit difference. And then we're also going to have this relationship, right? So now we also have to take into account, what is that noise? Okay. Yeah, like a really bad clarinet. I would know. No. Anyways, so then, right, so our pressure is the same as our Kc if we have no change in moles, in our gaseous moles. And so all this is saying, so our Kp is related to our same Kc concentration times RT to the power of our change in N. Or again, our change in N is then our difference between our number of moles of gaseous reactants and the number of moles of products, right? So products minus reactants, that tells us our change. And so that is the only little factor of difference between them, right? And you could imagine how that would change, obviously, your partial pressure if your moles of gas is also changing. All right, so then we can put this in practice. And so now we have that 2 equivalents of nitrogen monoxide. Again, note the gas phases for all of these, so that's important, right? Again, we're saying they're all gas phase. and all included in the expression. And so it's oxidized to nitrogen dioxide, and then we're given our Kp expression. And so how can we put it in terms of Kc? And I'll scroll back up so you can look at that relationship. So right, just start off, find your change in moles, and then you can go from there. So how is this one going here? So let's just start off with, well, what's our change in moles here?
It's the difference of 1 mole.
So n equals -1, right? So we have 2 minus 3. So good. So we have a change of -1 for our moles. And so right now we can just plug that in, not too bad. So we're trying to find Kc. So now we just have to plug in everything. So 2.2 times 10 to the 12th is equal to our Kc times, oops, sorry, I shouldn't have written Kc like that, times R. And so R is just going to be our good old gas constant, right? We're not in joules. So it's the 0.0821 for our ATM, liters, Kelvin, all that, times T. So of course, don't forget that T should be in Kelvin. So 298. And that, all of this to our -1. So let's just plug that in. So I get this for my Kc value. Let me know. You get the same, right? So I see chat has the same answer. And so yeah, we can round this to about 5.4 then times 10 to the 13 for our Kc there. Questions on that problem? So now let's look at this one. So now we just want to identify where does Kp equal Kc. So just take a moment to look at those reactions. So you're comparing A, B, C. right? What are you really trying to answer here? So what are we really trying to answer? So what are we comparing when we look at these equations?
Trying to see if the difference between the products and reactants equals 1.
And then what should we be looking at though? Because we have these solids and these G's. So yes, I just want to emphasize that we want to look at our gas state only, right? So you want to look at where the gas molecules stay the same number. And so I see chat has an answer. And so what do we find? So what do we find with A? So we have, so looking at this, right, you're just comparing our gases. So we have 2 equivalents of CO2 on our reactant side, 1 equivalent of oxygen on the other. So would this have the same Kp and Kc? So no. And so now we can go to B. So now we have, again, just comparing our gas, so 3 CO to 3 CO2. So would that be the same? So yes, and chat agrees. So this looks good. And let's just verify. And so no moles of gas on our reactant side. 2 over here. So, or excuse me, 3, I can't even add. So 3 moles of gas versus 0. So obviously Kp is not going to be equal to Kc there. Questions on this one?
What is KP and KC?
So remember, Kp is just when we use pressures, right? So if we were expressing these in terms of partial pressure versus expressing them in terms of molarity. And then again, right, we just see that, right, and let's kind of recap then. Because basically they were the same equilibrium expression, right? We just had this molarity versus partial pressure. But then we're saying that Kc is not always going to equal to Kp if your moles are changing, right? So then that's going to be changing your overall moles and can affect your partial pressure. So that's where we get that relationship from. Yeah, honestly, we probably won't see this too much, this relationship. Obviously, you need to know it, but yeah, we'll mainly probably stick to solutions, as we'll see. All right, so then this starts to get into our equilibria. And this will kind of help us for the next few chapters, or at least kind of understand where the expressions that we're going to talk about come up from. And so now we can kind of think about what this is saying. So if we have pure solids or pure liquids, then their overall concentration is not going to change. And so, right, so we're thinking of, like, let's say you have a pile of carbon or something, right? That would be not part of your equilibrium expression. Pure liquids, so we'll have H2O involved a lot in these acid-base reactions, but you're going to find that they're not part of our equilibrium expression since it's all in water. Or pure liquids, so we don't really talk about neat reactions, but I'll kind of put that where you're putting in, right, a liquid reagent. And so, of course, because our concentration doesn't change, then these solids and liquids are not included in our equilibrium expression. And so this is a little interesting one. So this is unusual because you don't typically measure gas and aqueous. This is a good one. So, right, we can start to get into what this is. So if we bubble CO2 in water, so that makes carbonic acid here, so you can have them, you can see the addition. And so here's our expression. And so this kind of gets into our acid-base chapter, or at least gives you a little tease. And so basically we're saying that our equilibrium expression is equal to our concentration of H plus ions times our hydrogen carbonate over CO2 there. And again, all these would have to be in molarity. So, right, even though it's a gas, this expression, it's in molarity. And then, right, our O2 is excluded since it's liquid, and it's our entire medium for our reaction there. And so again, kind of showing how that carbon has no effect. So looking at this reaction, so 2 equivalents of CO gives you CO2 plus carbon. But again, if you have this giant pile of carbon, it doesn't matter. It's all surface reaction anyways, so the amount of carbon does not affect our equilibrium. All right, now see if you can write an expression for this saying here. So what is our K? So just kind of evaluate, take a second. What is it saying? So what's our KC here? So what are my relevant products? So CO2, right, it's in our gas phase. And then any reactants though? So right, solid for our reactants, so the concentration is not going to be changing. So yes, we're just left with this CO2 expression here for our KC. So again, a little odd, but that is, right, this situation here. All right, so first, let's just write our equilibrium expression. Let's just do a practice. So write your expression for this equation. So hydrochloric acid plus O2 gives us 2 equivalents of water and 2 equivalents of chlorine gas. So what do we get for our Kc expression?
I got K sub D over RT cubed.
Oh, but just writing it like in terms of the variables here. Okay, I see it in the chat. So again, just products over reactants. And so again, right, we have our liquid here, so not relevant, but gas, gas, gas. And so it looks like chat has it down. So our chlorine squared over our hydrochloric acid to the fourth times O2 there. So that's just, again, our expression. Again, noting, right, to leave out our water. All right, so now this starts to get into basically what we're going to be doing from now until whenever. And this is also our lab today. So our lab, our equilibrium lab. So you'll essentially be doing this either Tuesday or Thursday. And so, of course, right, we want to find our equilibrium constant. And this always gets into the trickier part, right? It's much easier said than done to say, oh, yeah, we're going to measure the amounts of reactants and products. And so luckily, you're going to be doing a reaction that has good equilibrium and good color. So you have this iron 2, if I remember correctly. There's an iron 3 source. I think it might be an iron 3. So you're reacting your iron with thiocyanate to make this complex here of iron thiocyanate. And why this reaction works well for a lab is because, and you'll find this, right, this is a nice red product. And so you'll be able to make a calibration curve, measure the concentration, yada, 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 quantify it. And this is very yellow, so it doesn't really have much of an absorbance. And so, again, that's basically what you're going to be doing is, so, yeah, we have a way to quantify, right, our products with this lab setup. Again, right, like I mentioned, we'll do Beer's law calibration curve. And this, again, gets into, like, other methods, right? We could go back to NMR or sampling, aliquots, blah. So whatever way to measure reactants products, very situational dependent. And, okay, here's the key part, too, with our math, right? So our equilibrium mixture could have different amounts of reactants and products, but our value is always the same as long as our temperature is kept constant. So that will help us, right? So that means that we can just measure any amount, right, any equilibrium, as long as it's at equilibrium, then we have that same equilibrium and equilibrium constant. So that will help us. And so this teases kind of what you're going to be doing in lab and what we're going to be doing now and forever, essentially. And so stoichiometry can be used to determine our equilibrium concentrations if we know initial conditions and one equilibrium concentration. So that's exactly our lab situation, is we'll know initial conditions and we'll be able to measure our equilibrium concentration. And this is often, what happens. So usually, you're lucky to just kind of measure one of the concentrations, and then you might have to puzzle out the rest. And again, we'll go obviously through this process together, but we can figure out, right, from our equilibrium constants, our change, and then figure out the other chemicals, right, again, using stoichiometry. Okay, so that was a loaded statement. So let's go through this process. And so first, let's just set up our reaction here. So we're looking at CO plus 2 equivalents of H2 to give us methanol. And so then we're given some initial concentrations. So it initially contains 0.5 molar concentration of CO, 1 molar concentration of H2, and then we're given our equilibrium concentration. And so now we're going to be using these, I'm going to call them rice tables. So they call them ice, but yeah, everybody likes rice better anyways. And so I'm just going to rewrite this little table here. And so I like to say that our R stands for reaction anyways. And so we have, I'll just rewrite our reaction. So CO plus 2 equivalents of H2 to give us again our methanol. So our balanced reaction that we're starting with. And right, they gave it to us balanced. Just double check that it's balanced, of course. And so then the I in our yummy rice table stands for initial, so our initial conditions. And so now I'm just copying, and again, right, this is in whatever units you're in, so we're in molarity. So we have 0.5 molarity. They said we started with 1 molar concentration of H2. And right, we're just assuming that we should not have any products. It doesn't say we have any products. And so 0 initially. And so then let's get into our change. And so now we're saying, right, like how much is being consumed. And so if we look at our equivalents, right, we can look at, this is one equivalence. So this will be consumed by X amount, right? We don't know what X is. It'll be minus X. Then our H2, well, now we know that there's 2 of them, right? So they'll be consumed at twice the rate. So that will be minus 2X. And then whatever our change is, right, whatever our equivalence then, we'll make 1 equivalent of X there, right, for our products. Okay, so now this is looking good and kind of teasing to solving it. And again, all the math you're going to be doing. And so the last thing that it told us was at equilibrium, the CO was 0.15 molar. So now E for equilibrium. All right, well now we can start solving for things. And so from our table, right, this has our most information here. So we started at 0.5 molarity. We ended up with 0.15 molarity. So what was our X? What did you say? So 0.35. Perfect. So X equals 0.35. Okay, so now we can plug in our values for X, right? So, okay, if X is 0.35, that means that's our final concentration. And then, well, we have to do a little math here. So now 1 minus 0.35 times 2. And so that leaves us right with 0.3 for our equilibrium H2. And so now we can figure out where this is going. AKA now we're going to find our equilibrium constant. So we have our equilibrium concentrations. Let's rewrite our Kc if we haven't already done so.
What was that, 1 minus 0.35? How do you get 0.3 molar?
So solving for X here, right? So we have that basically that 0.5 minus X equals to 0.15 molar. So then if we solve for X, that gives us 0.35 there. So all we're saying is, right, 0.35 molar were consumed of our CO.
And then there was 1 molar minus the 2 times 0.35.
Yeah, so 1 minus 2 times, because we said we had 2 equivalents, so whatever X was being consumed at 2 times the rate. So yeah, that's how we got the 0.3 there. And so then we can plug it in. So now I'm just taking, right, our expression here, our equation, writing it as Kc, or writing our just generic before I plug in numbers. And so now that's our expression. So now we can plug in the values that we just found at equilibrium. So 0.35 over 0.3 squared times 0.15. And so now we can get our equilibrium constant for this reaction. Don't forget parentheses order of operation here on the bottom. And so that leaves me with about 25.93 for my Kc here. So it just barely favors our products in general. Questions on this one or this process or anything here? Because like I said, we're basically going to be doing this 100 jillion times until you're done with the CHEM series. So we'll continue on the third quarter too, this equilibrium fun. So you either love it or hate it. All right, let's try our next one. And so now it's saying that our reaction above was carried out at different initial conditions. And at equilibrium, this concentration of methanol is 0.11 molar. And so find the equilibrium constant at this temperature. So again, this is implying we're at a different temperature, so a different constant. So see if we can set that up. So just kind of repeat what we did before, and we'll go over it. I can scroll. I don't know how far out I can go, otherwise you can't see. So then let's kind of check in how we're doing, right? So again, I would just rewrite this reaction. That's all they said, right? We're doing the same reaction here again. Just different temperature, different initial conditions. And so again, right, it's because of the different temperature that we have to recalculate this equilibrium constant. So again, I'm just rewriting our reaction. And then, right, set up your initial conditions again. So 0.27, 0.49. And then write your change. So same concept. And right, we know it has to be moving in the forward direction. So we're going to do minus x minus 2x plus x. Because, right, we have no product, so we know it has to add x. And so then what do they give us? So at equilibrium, our concentration of methanol is 0.11 molar. All right, so what's x then?
11.1.
So 0.11 molarity. And so excellent. So now we can find everything from that. So 0.27 minus 0.11. So that gives us our equilibrium CO concentration. Repeat the same for H2, except write two equivalents, so minus 2x. So 0.27. And so now we have, right, all our equilibrium concentrations once again. And did we all get here? Kind of ask questions now type of thing. Because again, right, we're going to do this over and over. And so then last bit is just to plug back into our equilibrium expression. And so it's just the same as before. I'll rewrite it, right, with our variables. Products over reactants. And now plugging in our equilibrium values. And let's see, chat has an answer for me of 9.42. I think that sounds correct. I'll repunch it in right now. And just watch your order of operations and all that. So yeah, about 0.942, 943, something like that. Questions on that one? All right, so let's we'll start getting into this Q thing and what it means. And so Q is just basically what I like to call our snapshot. If I could smell. Yeah, that's snapshot of our reaction. And so basically, let's back up a second, because the thing about these two examples that was the same and that made it easy is that we had no products, right? So we knew that if it was going in any direction, it had to be going in the forward direction, right? And same thing, so we had only been given methanol, right? We would have known, well, it has to go in the reverse direction. So kind of the problem sometimes that we may encounter is that, let's just say, right, we're looking at a reaction mixture and we have reactants and products. How do we know which way it's going to proceed? And so this will help us for later potentially. And so if we have something to compare it to, then, right, we can look at our current ratios, kind of plug it into our equilibrium expression, and see how that compares to our constant. And all this is saying is it's basically the same K equilibrium expression. Right? They made it sound like confusing. Well, it's saying, right, it's products over reactants. That's K. Right? We're just saying that when we look at Q, we're not at equilibrium, hence why it's called Q. Does that make sense? And so then, again, right, we can see that, yes, our Q is just our same as our KC. I'll write that, right, same as our KC or KP expression. Again, Q is just giving us our snapshot. So I'll keep kind of emphasizing that. And so again, right, we have our reaction, so we can plug it into our equilibrium expression, knowing that it's not at equilibrium, and then figure out what direction our reaction may proceed in. All right, so then we get to this, which is kind of easier to look at our graph here. And so again, kind of the idea is, let's say we know our equilibrium constant. So in this case, right, it's 1.45 for this particular AB reaction. We don't really know what this is. And so all we're saying is if we calculate Q and it's less than K, well then obviously, right, it's going to want to proceed to the forward direction. And then if it's greater than K, right, then it's going to want to go back in the reverse direction. And so again, right, that's all that's telling us here in words now. So again, right, we calculate Q. If Q is greater than K, then all it's saying is it will proceed faster in the reverse direction, so trying to get back to equilibrium, and just saying overall that our products are decreasing and reactants would increase. So again, right, visually we're over here. And then if Q is less than K, then it needs to go in the forward direction. And so all that's saying is that, right, our reaction is faster in the forward direction, so our products will be increasing. And of course, if we find that our Q is equal to K, then all we know is that, yay, we're at equilibrium there. And then, right, this is just kind of saying what we were already understanding with our conditions. So, right, if we just have reactants, then obviously Q is 0 and it goes in the forward direction. If it's just products, then it goes in the reverse, which again is pretty, I think that's self-explanatory enough there. All right, so I think this is probably a good place to end here. So you can look at this, kind of think about where this is going to go, but I think I'll save it for Thursday so we can kind of warm up on it. And then we'll continue with kind of our equilibrium thoughts, right? So we're just kind of thinking, we're probably going to see different scenarios. We'll have to figure out, right, whether it's going forwards, backwards. But we'll dive into that more on Thursday. And again, that will be a continuing theme, so make sure you understand this equilibrium stuff. But like I said, we'll pick back on Thursday and give y'all a little refresher. All right, double check your grades. Make sure you get your quiz back from me and homework. And then I will see y'all in lab. Then, any last questions on stream before I end it?